All right. Hello, everyone. So, welcome to day 3. Today, we are going to talk a little bit more about log properties. We're going to bring back inverses, and then we are going to start the conversation about graphing logs. So, as we stated on the first day, the inverse of an exponential function is a logarithm, and vice versa. So this little flow chart that you see here is just sort of a quick little visual representation of what you're doing. If you are given an exponential and you switch x and y, which is what we do when we find the inverse, and then BAP this, it converts into a logarithm. If you're given a logarithm, and again, you switch x and y, and you lasso it, so 2 lassoed to the x power equals y, you end back where you started. So an exponential with a base 2 is a log with a base 2. The base of your exponent should be the exact same number as the base of your log. So log base 3 would be an exponential with a base 3, and so on. So that is the property that we are going to be using when we find the inverse of these, which essentially means if it starts looking like an exponential function, you're going to find and write it as a log. If it starts as a log, then you need to find the inverse, which would be an exponential. So remember, this little symbol means inverse. If the original problem starts as an f of x, then our final answer should say f inverse of x. If the original problem starts as a y equals, then we will write it as a y inverse. So f of x is just another way to say y equals. So really this is like y equals 4 raised to the x power. So step 1, switch x and y. So that would be my first rewrite. That will get you at least a point if you switch your x and y. But since it starts as an exponential function, the only place for it to go is to turn into a log. So you have to introduce the word log. Since this is a base 4, we will write base 4. The answer, now that I switched, is x, and the power is y. But I can't leave it that way because that makes it look like an original function, and remember we're trying to find the inverse. So since the original problem started as an f of x, my final answer would be log base 4 of x equals f inverse of x, and that would be how I'd write my final answer. So let's do another one that has some more going on. So step 1, switch x and y. So that would be step 1. All right, we have a base 2 exponential, so I'm going to turn that into a log with a base 2 of the answer, which in this case is x, and that entire power or exponent is 3y plus 5. Now we're definitely not done with this one like we were able to go right to the inverse on the last one. We have a lot going on. We have to subtract this 5 and then eventually divide by the 3. So if I start by subtracting the 5, notice that when I write this, that 5 is going to be written after my log. This is log base 2 of x minus 5 equals 3y. Then divide by 3, and I'm dividing the whole thing by 3. Since I'm sort of out of space, I'm going to write my final answer up here. Remember, the original problem was a y, so I'm going to write this as the inverse is equal to log base 2 of x minus 5, all of that divided by 3. That would be my answer for the middle one. Now, last but not least, we have the function equal to 2e to the x plus 1. So step 1, if this is a y equals, I switch my x's and y's. So there's step 1, my first rewrite. Now, again, this is a new situation, which is why I wanted to do this example. We have not had to deal with maybe any isolating first. This function technically is 2 times e to the y plus 1. So before I can turn this into a log, or a natural log, I have to divide by 2. Now that I have my exponential isolated, I can BAP it. So since we know natural log has an invisible base e. I'm going to write natural log. If you want to put the e, you can. It's why I wrote it tiny, tiny, but you don't need it. So log base e of the answer is equal to the power, which is y plus 1. Okay, y plus 1. We're almost done. We subtract that 1 over to the other side. So I get natural log of x divided by 2, subtracting 1. That would be equal to y. The original problem was f of x, so I'm going to write that as f inverse of x. So given an exponential, your final inverse will be a log. If it starts as a log, then you have to convert that into an exponential. So you're going to start the same way, switch your x's and y's. And then since it's a log, you can lasso it. So start with the 6, loop it around the x. So it's 6 to the x power equals our inverse. So f inverse of x. So started as a log, ends as an exponential. Starts as a log, so our final answer should be an exponential of some sort. So again, this is y equals, so let's switch. Log base 3 of y minus 5 plus 2. Okay, and very similar to number 3, we have to do a little bit of isolating on this one. So before I can do any lassoing, I need to isolate the log. So I'm going to subtract that 2 over. So we have log base 3 of y minus 5. So all of that is part of the log. So please don't divide by y minus 5. Don't add 5. That is what we're taking the log of. So now that the log is isolated, I can lasso that entire thing. So it's 3 raised to the x minus 2. So base, answer, now the power. So this is going to be, I'm sorry, not base answer power. I'm lassoing the log here. And now my final step is add the 5. So 3 to the x minus 2 plus that 5, that equals my inverse. All right, last but not least, this is a y. X equals natural log of 5 plus the square root of x. And notice it's in the parentheses, so there's nothing for me to isolate on this one. There's nothing being added or subtracted, and there's nothing being multiplied out front. So our invisible base is e, so when I lasso that, it will become e to the x power equals, oh, wow, I'm really doing it today, huh? There we go. E to the x power is equal to 5 plus the square root of y. And now I want to solve for y. So subtract the 5. And to undo a square root, I have to square it. So this would be e to the x minus 5. All of that squared is equal to my inverse. Once I have y isolated, that represents my inverse. All right. So on day 1, we did talk about how the graph of a logarithm looks because it's the reflection of an exponential function, and it's the reflection over that perfect diagonal y equals x. So that means every single point from an exponential function, like this dot and this dot and maybe this dot, if I were to switch those coordinates, so this would be what? 0 up 1. This point would be 1 comma 3. This point would be 2 comma 9, and so on. If I were to switch those, it would go through this dot. If I switch 1 and 3, it would be 3 comma 1, which would be right here, and 9 comma 2, which would be right here. So the graph of an exponential, you just switch those coordinates to create your log. So what is the line of reflection? We said that on the first day, y equals x. What point do all logs have in common? That this dot, all logs will have in common as long as there are no transformations. And since we know for an exponential that there's an asymptote that's a horizontal asymptote, okay, right, x on the x-axis here, when we reflect that over this diagonal as well, all of our log functions are now going to have a vertical asymptote at 0. So all of these points from this dot and close to the asymptote are all of these points that have been reflected. Now these points do show up on a calculator, but unfortunately, these dots that are in this section of our logarithm do not show up on a calculator very nicely. And so what ends up happening is your graph, so I will type this in and then I'll show you how to do it yourself. Log base 3 of x. If I were to graph this in my calculator, it kind of makes it look like the graph stops right here. And the only reason why it looks that way is because the screen only has so many pixels to be able to plot. So this is trying to represent that this is curving downwards along the y-axis, but it can't ever touch the y-axis. So there's literally only so many little blocks that it can plot before it's like, okay, I'm out of space. So that's how we have to keep in mind that a logarithm is the reflection of an exponential. An exponential never stops. It just kind of skates right above its asymptote. So this log has to skate down its vertical asymptote. So let's actually graph using our calculator this log base 3 of x. So to get that log base, you're going to press math, then alpha, which is the green button, and then math again, and that's how you're going to change the base. So if you go here to your y equals screen, press math, alpha, math. So math, then the green button, and then math again, and that should bring up log base. If yours does not allow you to do that and it says it's disabled, please bring it to your teacher so that they can take it out of test mode and enable it so that you're able to do this. So when I go to my table, since my calculator is based off of x values, all of our calculators are, it's only going to give you integer x values. So 1, 0. So let me write my little table down here. We have 1, 0, 3, 1, and as we kind of stated at the top of the page, 9, 2. So if I plot that 1, 0, 3 up 1, and 9 up 2, in my mind, that looks like a square root. That's exactly what a square root function would look like. But looking at my calculator, there's this tiny little piece that is showing that is below the x-axis that is not represented by these points. And that's because there are infinitely many numbers between 0 and 1 of a logarithm. So we just have to be a little bit smarter than the image that shows up in our calculator and just connect those in both directions. So it does curve slightly upward forever. This curves slightly close and closer and closer and closer to this invisible vertical asymptote at x equals 0. So when we're talking domain and range, remember it's the inverse of an exponential. My domain is now restricted to go from 0 to infinity. My range is going to be my all reals. So this gets ever so close but never equal to 0, and then it goes to the right forever. My range goes to the bottom and to the top forever. So my end behavior is precisely my domain and range. As my x goes to the right, my y values should, as my x goes to the right, my y values go up, but as my x goes to the left, it doesn't go to negative infinity towards the left, it goes towards 0, and my y values go towards negative infinity. So what is the inverse of g to the x? Well, since g of x is a log base 3, step 1 is switch x and y. Okay, switch x and y. It starts as a log, which means we can lasso a log. So we're going to start at the 3, loop it around. And if you're getting the hang of that and you're like, oh, I'm starting to see a pattern every single time that whatever this bottom number is, okay, whatever the bottom number of my log is, this 3, that's the same as this bottom number of my exponential. It's literally this. Just an FYI. All right. So my last little thing I have to talk about today is when we are trying to find some transformations that happen with logs, we want to put it in expanded form. A lot of times it's represented called general form. Whenever you see general form of a log function, that should trigger the word expanded. And so if I look at the general form of a log, I notice there are some familiar letters like A. We know if a transformation has a number out front and it's greater than 1, it's a vertical stretch. And if it's between 0 and 1, it's usually a vertical shrink. If within our function that's impacting the x's, if it's plus h or minus h, it could go to the right or to the left, depending on if it's positive or negative in there. And last but not least, if something is being added or subtracted at the end, we know that that shifts it up or down. So you are perfectly able to move that k if you don't like the way that it looks in front. You are more than welcome to rewrite it at the end. And so now that it's at the end, hopefully that looks kind of familiar to all of our other transformations. Like when we did, let's say, quadratics. Okay, that's an h. That looks just the same. Instead of being squared, it has the word log in it. When we do square root functions, looks just the same. It's doing the same thing. So again, k is our up and down, h is our side right and left, and a is either going to be a vertical stretch or a vertical shrink. But the only way to get these transformations is if we write our log in expanded form, which taps into the rules from yesterday. So yesterday, we said if there's an exponent within a log, what it needs to do is pop out front and become a coefficient. So this would be g of x is equal to 3 log base 2 of x plus 2. That is as expanded as I can make it because the only other rules we have are for multiplying and dividing. We don't have any rules for adding. So this is as far as I can go. Now that I have it fully expanded, I'm noticing two transformations. We have a vertical stretch, and we have a left 2. So if our graph, okay, is going left 2, that is super important to us. Because now that we are graphing logs, and logs have a vertical asymptote, and we're shifting the entire thing to the left, so because of the shift left 2, the asymptote is also shifting left 2. So instead of x equals 0, it's going to be x equals negative 2. So it would look kind of something like this. It would shift over, that would be the asymptote, and it would be something like this. Okay, that's kind of the sketch-ish. So let's try another one. Number 10. Express it in general form. So again, general form just means expand. Expand it out and see what your transformations are. So we have log base 2 of 8, and then yesterday we did subtract log base 2 of x. Log base 2 of 8 is really saying 2 to the what power is 8. But now that I showed you this math alpha math, you could just type log base 2 of 8 now and hit enter in your calculator, and that's just equivalent to 3. If that looks a little backwards, you are welcome to rewrite it so that it's negative log base 2 of x plus 3. Now notice this plus 3 is not inside of our parentheses like the last one. So it is not the same type of transformation. We have a reflect over, we'll just say reflect. And this is going to go up 3. For logs, we don't really care if it's being shifted up or down. We only care if it's being shifted right or left. So since it did not get shifted right or left at all, the asymptote is going to stay at 0. So it would still look something like this. It would just get reflected. Something like that. All right, and last but not least, in general form, so we are going to expand to the best of our abilities. So we have negative parenthesis log base 4 of 2 plus log base 4 of x. If you're wondering why I put parentheses around it, it's because the entire log has a negative in front of it. So though I'm expanding it, that negative has to apply to everything within that log. All right, log base 4 of 2. Again, if you can figure out in your head, that's great. Log base 4 of 2 is 0.5 or 1/2. So we have negative parentheses 1/2 plus log base 4 of x. We are going to distribute the negative. So we will get negative 1/2 minus 1/2 log base 4 of x. And then I'm just going to do a quick little rewrite. Oh, not 1/2. Sorry, guys. Just a negative. All right, rewrite it. So negative log base 4 of x minus 1/2. So again, we have two transformations. We have another reflect over the x-axis, and we have a down 1/2. Again, no transformations are happening within the log, so my asymptote is still at 0. All right, see you next time.